Hi, another quick video podcast, this time on elastic strain energy. First of all, we'll just deal with a simple material that obeys Hooke's law. The dimensions of force in newtons times distance in metres is Newton metres, and Newton metres are the units of joules. So any piece of area on this graph represents energy. So this total area here represents the work done stretching the material, and if the material is perfectly elastic, it also represents the energy stored in the material. Clearly that's a triangle in shape, and we know that the area of a triangle is a half base times height. So the energy stored, or the work done stretching the material, is a half F delta L. Gets a little bit more complicated, not too much so, if we start imagining a situation where the material ceases to obey Hooke's law. You might see again an initial straight line, but then we might see the characteristic curving over for a region of plastic deformation. Now, this total area here represents the work done stretching the material. But that's not the same as the energy stored anymore, because it's plastically deformed. When we remove the weight, it will return and have a new have a permanent extension. The energy stored is now this area. That's the only energy we got back when we removed the load. And then this area here, I'll cover shading with wiggly lines, is the energy that's been dissipated or wasted, permanently deforming the material. So that energy is lost. And I'll just briefly now get you to think about, if we did the same thing, just going back to the simplest situation, but we replace this by strain and stress. So stress is force over area, and strain is delta L over L. F times delta L again will represent the work, because it's force times distance. Cross-sectional area times length is volume. So this area now is the work done per unit volume. I hope that helps you. Thank you.